name is Yijing Watkins from Los Alamos National Lab. So you guys probably heard about the Telluride workshop. So I was lucky to attend it last year as a student. And then when I was there, I discovered Yijing also used locally competitive algorithm as their sparse solver. And that's what we're using in my group. So, but it doesn't support directly online dictionary learning. So I'm interested in solving this issue. So in this presentation, I would like to demonstrate our spiking LCA module is able to support online unsupervised dictionary learning by using only local computation and the unsigned values for the spiking rate, which is compatible with the constraint from the Yijing model. First, I would like to give a brief introduction of what's sparse coding. Sparse coding was introduced by Olhausen and Few in 1996 to mimic how brain is processed visual information. So it turns out when brain gets the image, the first thing it does is looking for edges and lines, those board-looking features. So sparse coding is an unsupervised feature learning algorithm to mimic how the one stage is processed those image by looking for edges and lines. And it uses an complete set of feature vector, which also I could call dictionary, to find or solve for sparse coefficient or sparse code, which contain as much zero as possible can be accurately infer or reconstruct the image. So in order to solve with sparse code, we need to minimize the following energy function. It contains the two important parts, the reconstruction term, which is the difference between input I and the reconstruction, which is the linear combination between the phi and the t of u, which is the sparse coefficient. And we also have the sparsity penalty term to make sure we have as much zero as possible for the sparse code. And then U here is the memory potential in the neuron, and the T here is the threshold, or we usually use for the non-spiking model, the soft threshold because it's convex. There are many ways, many different techniques to solve for sparse code. So in our group, we are focused on using locally competitive algorithm, short for LCA. It was first introduced by Rosell in 2008. And then I list the original Rosell's model here. It contained two layers, the input layer, and then the T of U, which is the sparse layer. And then, so the LCA dynamic can be expressed as a differential equation I listed here. So it's the leaky integrator of the input, which is I times transpose of V, and then lateral inhibition. So this model also can be called as a lateral inhibition model. It works as a dynamic sparse solver when the dictionary is provided. So it doesn't directly support dictionary learning. And then I believe that's also Yijing uses for their sparse solver. So I would like to solve our group would like to solve this issue. So the most natural way occurred to us to allow dictionary learning is to apply directly stochastic gradient descent directly to the energy function here. And turns out in order to update the phi, the dictionary, it's just a Hebbian updates between T of U and then with we call residual layer. Residual layer here can be defined as a difference between the input and then the reconstruction. So here's our implemented model, the final model. So we can actually, so we're adding the residual layer between the input and the T of U. So we're allowed to do dictionary update through the Hebbian plastic connection between T of U and the residual layer. And additionally, we discover we can do this lateral inhibition through the residual layer as a two-step process. So this final model is more memory efficient because you only have to store phi and compute the transpose phi every time. And most importantly, it support online dictionary learning. So there are different applications, there are many papers that's published on the previous spiking LCA model. So we would like to, this slide, the next slides, I would like to introduce a couple applications we like to immediately implement on Yijing if we're able to visually map our spiking LC model into Loihi. So the first one is the live event-based video interpolation. So you guys probably heard earlier the event-based camera. So we want to connect the DVS camera directly to Loihi. So the DVS camera usually will output an on and off response when there's a pixel intensity changing occur in the scene. So if we're able to train a good set of dictionary, a linked dictionary, when I say linked dictionary here, it means a set of dictionary that share the same sparse representation, we're able to estimate like the higher resolution of videos based on the low bandwidth, low power, lower quality event-based camera videos. So you can see the reconstruction, there are some still artifacts there, but you can definitely extract more information comparably to the on and off response from the DVS camera. The second application we'd like to try is online depth sensing. So if we're able to also train a good set of linked dictionary based on the event-based camera, like DVS camera or the stereo camera, to put on the robot or in space or underground, and then connect to Loihi. Turns out the neurons from the LCA layer are depth selective. So here is the neurons if we train a good set of dictionary. So here's the neurons and we look at the activation corresponding to this neuron. This actually corresponding to the nearest thing, and this is the furthest thing without the label. And if we allow lateral inhibition. So, but if we remove the lateral inhibition, the neurons are no longer responsive to depth. And even we put a threshold into them, they're still not responsive to depth. In order for us to do those, I think, useful applications, we want to officially map our algorithm to Loihi, we need to respect all the major constraints exposed by the Loihi model. And here I list all the major constraints, and then I will propose our corresponding hackaround solution to that. So, the first constraint is caused by computation locality. So, the connection from the residual layer back to tier view. So the transpose phi, we're not allowed to perform transpose computation anymore. So it's non-local. So in that sense, as a solution, we allow the bidirectional Hebbian plastic connections as a separate learning connections from tier view, between tier view and the residual. But we initialize them transpose to each other. So instead of transpose phi, we actually have psi as a transpose phi. So things is the Hebbian dates. So the updating of the update of Hebbian updates is based on the same set of pre and post layer. So the connections, the relationship should stay the same. Second constraint is also caused by the same computation locality constraint. So we cannot do weights normalization during the weights update. So that actually causing two actual problems. Because first, we're not able to calculate the self-interaction correctly. So every time a neuron spike, you would not only inhibit the surrounding neuron, but itself. Second one is, so due to the nature of the sparse code, it tends to always reconstruct the image. So it's always a positive or negative bias in the error layer. Over time, the weights will grow massive. So since there are two problems, we have a two-step solution to that. First, every time a neuron spike in the LC layer, we immediately lower the LC threshold, and we slowly increase the threshold towards the original one. So in that sense, we promote the neuron just spiked to spike again, all competitions between neurons. Secondly, we actually put a weights decay during weights update, and then the decay rate is proportional to the weight value. So the weight with higher values would decay faster comparably to the lower one. And then constraint 3 is, since it's a spiking model, so we only allowed to have positive firing rate. And so we establish a positive baseline rate to encode both positive and negative firing rate. So it's above baseline is positive, below is negative. And the last constraint is low precision weights update. So, so we haven't officially tested these constraints on the spiking model, but we did for the non-spiking model. But everybody, if you're familiar with sparse coding, you know it's very robust to noise. So the feedback loop between T of U and the residual is promote homeostatic equilibrium, which works similar as the tractor dynamic. So even with low precision, we are not going to get to the
conclusion, please.
Oh yeah, sorry. Oh, I'm going to go to my result. So this is the spiking unsupervised dictionary learning and sparse solving result. So here is the evolution of dictionary converging over one epoch. You can see initially it's gray because that's our baseline, and in the end you can see more Gabor-looking features. On this side, it shows by using the converged dictionary, the frame-by-frame sparse solving procedures, and the left column is the spike train. So, and then the spike train is pretty much the low-pass filter of the spike train. You can see it's not perfect, but we can definitely see a car as a reconstruction. So as a general conclusion, so I first proposed our implement LCM model that support online dictionary learning. And then I show you some two, I think, useful applications we can use if we're able to fully map that on Louis, we can try next. And then I show you the major constraints exposed by the current Louis module and our corresponding solutions to that. And then in the end, I show you the dictionary learning and then a sparse solving result.
Okay. Thank you. Okay, thank you, speaker.